Here, we discuss the use of Shapley values to interpret feature contributions in a black box machine learning model. This is, however, not the origin of the Shapley value, since Shapley was an economist interested in game theory. Therefore, let us first focus on the game theoretical concept of the Shapley value to get a grasp of how it works. Basically, the Shapley value represents the payout for every player in a cooperative game. It can, however, also be used to measure the contribution of a feature to a machine learning model. As a side note, Shapley won the Nobel Prize for his contribution to game theory. The original context of Shapley tries to assess each player's contribution in a cooperative game. Let's take a simple example: an indoor soccer team, futsal. The goal is to find out how much each player contributes to the team. In game theory, this would be the payoff, but we could call it the marginal gain or contribution of each player. We assume that we have a characteristic function to assess the value of a soccer team. Adding one player to the team will give it a certain strength. Adding player A will give the team a value of 6. Now, we can try to complete the team by adding extra players. Adding extra players will increase the value of the team. However, players can have overlapping skill sets. Say that adding player B to player A gives us a value of the characteristic function of 10. Hence, B has a marginal contribution of 4. Adding player C increases the value to 12. So C contributes only 2 to the team. However, if this small value is due to player B already being in the team before C, then we should take into account what would happen if C came in first. This is the only fair way to address all players' payoffs. So when we add C first, her marginal contribution now is 4, and that of B is reduced to 2. If we want to be perfectly fair in our assessment, we should then look at all possible teams we can form with player C to know what value she really adds to the team. In other words, to know the contribution of C, we need to average her contribution in all formations of the team. To explain this, we will need some combinatorial theory. However, let's first go over some extra intuitions. This will make it easier to explain the math later on. First of all, it is important to see that only the players in the team before C matter, not the order in which these were added. Whether A came first in a team or B doesn't matter. This means we only need to know the value of adding C to a team with A and B once and weigh it with the number of teams we can form with A and B. The second notion is that all players that come after C are not important, but we need to take into account that we could add players D and E in a different order and it would not impact the marginal contribution of adding C to a team with A and B. So now we have to translate this intuition to a mathematical formula, as you can see here, where phi of j represents the contribution of player j and x1 until xp represent the players in a team. It is a quite intimidating formula, so let's break it down in little pieces. We have a team with p players and we want to know the payoff for a player j among those p players. This means we have to look at all possible subsets where we can add player j to the team. Put differently, we take sets of players out of all p players, not including player j, since this is the one we're adding to the team. So let's work this out again for player c in our soccer team. In other words, we consider all possible teams with players A, B, D, and E. This can be teams of all possible sizes: AC, ABC, BDC, AEDC, etc. Note that also the empty set is a subset, this is the value of a team with only C in it. We saw earlier that the order of the players in the subset didn't matter. However, if we want to weigh the contribution of C over all possible teams she can be added to, then we need some combinatorial theory to determine the weights. Again, recall that C has the same contribution whether the team was AB or BA before she was added. All permutations of players in the team before C are given by the size of S factorial. B minus the size of S minus 1 is the number of residual players left after adding C to the subset. So the factorial of this term gives all permutations how we can add these players. B factorial is a normalization and corresponds to the total number of teams possible taking the order into account. This is the denominator of the weights. The actual contribution of C, respectively J, is then the value of the team with C, respectively J, minus the value of the team without C, respectively J. We just need to calculate this value for all possible teams. In other words, the Shapley value of player C is her marginal value over all possible subteams and weighted over all possible permutations of these teams. Now let's translate the problem to a machine learning context. Suppose you have trained a machine learning model on your data. We want to know how much each feature contributes to our model's predictions for a specific observation. Here, f hat is the estimated function by your machine learning model. Think of a random forest neural network or SVM. xs is the subspace of features. To obtain the estimate of the model over a subset of parameters, you will have to integrate out the other parameters that are not in the subset. In other words, marginalize for the features that are not in the model. The contribution is then the difference of this prediction from the average value or the prediction of the null model. The average value is often just the mean value of your target in the data, sometimes also called an intercept model. Note that if you subtract two value functions for different subsets, this baseline term actually disappears. All possible subsets of feature values have to be evaluated with and without feature j to calculate the exact Shapley value. Obviously, this becomes an exponential problem when there are many features. Therefore, an approximation based on Monte Carlo sampling is often used in practice that samples from the feature space, as you can see illustrated. In other words, for every feature j, we sample big M times a random permutation of the other features and calculate the differences in predicted value for a specific observation. The Shapley value is then the average of all these samples. Let's illustrate this into somewhat more detail. Here you can see a worked out example of how to calculate the Shapley value. Say we have an observation X, BART, with features age, income, R for recency, F for frequency, M for monetary, and debt. Assume we want to determine the importance of F for BART. We start an iterative procedure for M starting at 1 and going to big M. We draw a random instance Z from our data. Say this is Tim. We then choose a random permutation of the features, say R, debt, F, H, M, and income. The first table illustrates the values of these features for Bart and Tim. We then construct two new instances. The first one, X plus J, includes all the values of R, debt, and F for Bart and the values of H, M, and income for Tim. The second instance, X minus J, includes the values of R and debt for Bart and the values of F, H, M, and income for Tim. We then calculate phi of Jm as the difference in the prediction of the machine learning model for both X plus J and X minus J. Once the iteration has finished, the importance of feature j for x can be calculated as the average of the phi jm values.